I want to start this block by explaining why we want to do overloading in Haskell. And that's in the context of a discussion about type classes and instances, which is the mechanism we use to support overloading. And then I want to talk about the built-in types and type classes that Haskell comes with. So many of the basic types are bound up with a fairly complicated set of type classes, and they're interrelated to each other, built on each other. And once we've done all that, I want to talk about type checking, how we ensure that the programs we write have an appropriate type, and how we can deduce types without actually writing them down for functions. So I'll talk about that. I'll talk about that in the context of monomorphic, but also polymorphic types. And that brings us to the topic of unification. And finally, we'll look at how this all ties together with type checking when we're involving type classes. But let's just go back to the beginning and talk about why we might want to have type classes. So we talked already about polymorphic functions like map, where the same code, the definition of map that you see there, given by a list comprehension, the same code works for different types. It works for any input type and any output type, and takes a list of the input type and returns a list of the output type. And so we get fantastic code reuse and comprehensibility, because we just see one name map for all those different uses at all those different types. Now we're using the same code at different types. It would be really convenient to use the same names like equals for equality, or plus and show for functions that do similar things at different types. But that would mean they have different code at each type. So for example, with equality is built in for numbers. For algebraic types like bool, we define it from scratch or we derive it. And for something like a list of type A, we define equality for that using an equality on the type A. And this process of using the same name for different but related similar functions is called overloading. Now, why do we want to get overloading? Well, if we are able to use the same name for equality functions over all types, we get code reuse. So we can write, here's a definition of a test for y being an element of the list x's. That single piece of code will work over all list types when the base type A has an equality function. So what we need to do somehow is express that informal has an equality function somehow inside the type mechanism of Haskell. We'll turn to that in a second, but just to reiterate, we're using that single symbol for every equality function, rather than the alternative would be to perhaps have a subscript on the symbol. So plus int, plus integer, plus float, and so on. So we get, those are harder to read, and also we get no reuse from that. So you can see that we're able to use that single definition if we're able to overload symbols like equality. So what we'll do in the next segment is explain the mechanism we use for doing that.